This is Mr. Beck Does Your Homework. This is AP Physics Homework 12.1, questions 3 and 4. Little tricky. Light of wavelength 536 nanometers in air enters a fishbowl filled with water, then exits through the crown glass wall of the container. What is the wavelength of the light in the water? I've got an index of refraction of water and an index of refraction of crown glass. So the first thing I know is that my wavelength is 536. Now it says nanometers, that's times 10 to the minus 9. So times 10 to the minus 9 meters. I know that it starts in air, and the index of refraction of air is 1. Now I'm given some other indices of refraction. I'm looking for wavelength, so I want something that relates the index of refraction to the wavelength. I don't have anything yet. What I know is that my index of refraction is the speed of light in a vacuum divided by the speed of light in the substance. I also know that that any wave has a speed equal to its frequency times its wavelength. Now, in these cases, I've got a couple things that are always going to be constant. That's the speed of light, and that's also the frequency, because the frequency depends on the source. Once I've got that frequency, it's going to stay the same. So let me combine these two equations. Here I've got n equals c over v, so that means that v is going to be c divided by n. Over here, I've got v equals f lambda, so I can write c over n equals f times lambda. If I gather the constants together, so again, c is going to be constant, and for that particular ray of light, f is going to be constant, then what I can wind up with is c divided by f, which is a constant, is going to equal n times lambda. So if c over f is constant for n and lambda, well, here I've got an n of 1 and a lambda of 536 times 10 to the minus 9th nanometers, and that's going to equal this constant. If later I go into the water, well, the water has an n, and I'm looking for the lambda for water. So again, it's n lambda, but they should be the same constant because those are constant c over f. So let's take it over here and write that n1 lambda 1 is going to equal n2 lambda 2. So now, since they're both equal to the same constant, c over f, and the frequency will be set as soon as I get going, so now I've got n1 lambda 1, that's going to be here, n1 lambda 1, is going to equal n2 lambda 2. Well, here's the n I'm looking for, 1.33, is going to equal lambda 2, and I'm going to solve for lambda 2. So this relationship is going to be very helpful later on. So if I wanted to do it in this case, I would say 1 times 536 times 10 to the minus 9th equals n2. For me, that'll be 1.333 times lambda 2. And now I can solve for lambda 2. It does say answer in units of nanometers, so if I was smart, I would not even include the times 10 to the minus 9. I could just have 536, because if I want to answer in units of nanometers, I can just leave it in that, because now I've got n1 lambda 1 equals n2 lambda 2. If I put in lambda in nanometers, I'll get out lambda in nanometers. So if I'm smart, I'm just going to leave out the 10 to the minus 9, and then I'll get lambda 2 in nanometers, and that's what I'm looking for. Same thing for part number 4.